Hello, welcome to our course on solar electric energy systems. Just give you some introduction today and we discuss about solar irradiance and its properties. First, some formal things. It's usually a course with presence, but this time we do an online course. Upload the videos on Mondays during the official lecture times from 11 a.m. to 12:30 p.m. The exercise will take place after that at 12:30 p.m. until 2 p.m. There will be an examen, maybe also a small test in between, but the main examen will be in July this year and the exact date will be announced in May 2021. We put the videos on YouTube. Unfortunately, the Paul and Panda platforms are a little bit, don't have enough capacity for putting on these long videos. So you have the links to YouTube also on the Panda and Paul platform. And the lecture notes and the presentations are provided as PDF files, also via Panda and Paul platforms. There's also consulting hour each Tuesday from 10 to 11 a.m. You have the Zoom link here, and so you can ask me questions or give comments. Also, if there are some questions and comments of general interest, you may add them directly at the YouTube videos. Also, you may add a like if you like the videos or give suggestions for improvements. My name is Stefan Krauter. I'm from the University of Paderborn. We are the group of electrical energy technology, sustainable energy concepts. The web page you find here. What we do some research on sustainable energy generation and the sustainable use of energy. We do examinations on energy efficient buildings. We do wind power monitoring. We do decentralized energy systems. We do virtual energy storage. We do load shifting via remote control of loads. So this saves energy storage and therefore we call it virtual energy storage. And we also work on energy yield prediction and optimization of PV. And since a couple of years, we have a micro inverter lab where we examine the different micro inverters, how good they perform in the lab and how good they perform outdoors. My name is Stefan Krauter. I did my master's at the University of Technology Munich. During that time, it was called still a diploma in Germany. So I received the title as a diploma engineer for electrical engineering and information technology. Then I did a PhD on photovoltaic module modelization at the University of Technology in Berlin in 1993. After that, we founded a company for manufacturing PV module. It's called Solon. It was called Solon SE now. I carried out habilitation. In order to get a university professor in Germany, you have to carry out a kind of second PhD, which is a bit broader, and this is called habilitation. Then I'd been for almost 10 years in Brazil, first at the Federal University in Rio de Janeiro, then at the State University in Fortaleza in Ceará. During that time, we set up renewable energy labs and we organized some events called Rio 02, Rio 03 and so on until Rio 15. There's also a web page. I think the last one was www.rio15.net. The one before was www.rio12.com. In 2006, we founded the Photovoltaic Institute in Berlin. While photovoltaic got considerably cheaper, we thought also about the quality of photovoltaics and the lifetime. And so we practice mainly quality control there. So this was testing and certification of PV modules and systems. During the period from 2008 to 2010, I'd been professor at the University of Applied Science in Biberach in southern Germany. And since 2010, I'm a professor and chair at the University of Paderborn. I'm also vice director of the Competence Center for Sustainable Energy Technology. The abbreviation is KET. give you an overview of our lecture. So today we will start with the potentials of solar energy, the properties of solar irradiance and shadowing issues. Then the next lecture we will talk about solar concentrators and solar thermal energy systems. Then we will talk about the principle of photovoltaic energy conversion, the manufacturing, the making of solar cells, the characteristics of photovoltaic energy conversion devices. It means solar cells, but also solar modules and solar power plants. We talk also about the manufacturing of solar modules, its characteristics and its performance. The PV systems. We also consider wiring, the inverters, the grid-connected system configurations. Then in the second part of PV systems, we also consider mounting, so-called BOS, that means balance of systems costs. Then also we talk about the difference between off and on-grid PV systems and the related costs. Then we take a look at the market. We take a look first at the off-grid market, which has been the traditional market of photovoltaics 20-30 years ago. Then the markets triggered by so-called feed-in tariffs or premium tariffs, FET, the self-sustainable markets, and the actual cost and price development, also compared to other energy technologies. Then we talk about the performance, how we can optimize that, the optical, thermal, electrical performance, simulation, measurements. And then we talk about the durability of photovoltaic modules and systems. So we talk about the standards, the different tests we have, and the different degradation effects. Then we talk about a very important issue, that's energy storage, because the price you get if you directly feed into the grid without any giving any security of supply is getting lower and lower. So the utilities and the consumer demand a constant power flow, and therefore you have to buffer it via energy storage. So we take 2 lectures about energy storage, and at the very end we talk about the more bureaucratic procedure of the setup of large-scale PV power plants. Let's start. Just first, it's your turn. I want to have a guess about the present contribution of solar energy to our living. What do we guess? Is it 1%? Is it 5%? Should make a stream and get some reply immediately. Or is it 20%? No, it's actually 94%. How can this number occur? Solar energy contributes 94% to our planet's energy use. It warms up the Earth from its space temperature, minus 273.5 degrees, to 14.5 degrees positive, and thus Celsius. And thus it enables life. Without the sun, it would be rather cold. If we would do that artificially, with artificial energy sources, we would need about 15 times the commercial energy we use today. It's about 15 times 429.4 exajoule. Remember, exajoule is 10 to a power of 18 joule. A joule is 1 watt second. And that is 15 times. So our energy need would be 15 times more, and therefore we only have to supply it one time 429.4 exajoule. That's our present world energy consumption. So if we talk about other forms of energy, the fossil resources such as coal, oil and gas are deriving from photosynthesis. Our planet has absorbed sunlight for hundreds of millions of years to create all those fossil fuel resources that last now only for just 200 years of industrial human civilization. We have a problem with the very fast emission of carbon dioxide. Everyone knows that. It's called the greenhouse effect. Carbon dioxide is transparent in the visible range, but not transparent in the infrared range. so it lets the sunshine in, the sun gets absorbed, the Earth's surface warms up and is also emitting radiation. There's also a black body, so it's emitting radiation, but in the far infrared, in the frequency range of, or wavelength of about 10 micrometers. And this is partly blocked by greenhouse gases such as carbon dioxide, but also methane and other gases. There have been a lot of investigations during the last decades on that. These are some simulations. What happens if we go on emitting carbon dioxide at this level? You see that the different research institutes, they predict that the temperature will increase from 2 to 5 degrees Celsius. Okay, if you live in Germany, you say, okay, 2 degrees, that's nice, it's a bit warmer, but for the rest of the world, this can have some severe problems. What happens? So this is some MIT research. So they say, okay, we have some kind of threshold, therefore it's marked in red at 2 degrees Celsius. Before that, the issues are rather small, but then there's called some tipping point. It's called some tipping points. Then suddenly the impacts will be rather big. Let's talk about the crop yields. So without any artificial irrigation and so on, the crop yields fall due to the temperature increase. Also, what we observe now, that the glaciers are melting worldwide. Also, we also perceive in some countries, such as Africa, but also Latin America, some water shortages. And if it goes beyond that, we will have rising seas because some of the ice on the pole caps is not swimming like in the North Pole and the Antarctica. It's on fixed ground, and if it's melted, it rises the sea level. Additionally, the expansion of the water due to higher temperature also rises the sea levels. What we perceive also now, we have reefs damaged by the absorption of partly absorption of carbon dioxide in the oceans, and these damage the reefs. You can also see already in Australia, these famous reefs are all damaged. And also we have species extinctions that already happens now, but will be further increased. What we also see now at the weather, so we have more storms or more heavy storms, we have more droughts, more fires and heat waves. Additionally, because the oceans gets warmer, we have also more rain, but not evenly distributed rain. We have some very heavy rain for a very short time, but it's not sufficient really to sustain agriculture. They have long periods of droughts mixed with very short periods of heavy rain. Also, there could be an abrupt climate change. We perceive this already in Russia. The so-called permafrost, permafreeze regions, they are already melting. And in these regions, there's a lot of methane contained. And this methane gets set free and additionally increases. So there is a positive feedback loop in that, and it additionally increases the greenhouse gas effect, because methane is about 25 times more effective in the greenhouse effect than carbon dioxide. So what can we do? So here we have a representation of the world's energy consumption during 1 year. This is represented by this small cube. So remember, in the first slide, it was 429 exajoules. This is the world's energy consumption during 1 year. Contrast, we have all the known resources. For example, gas, you see it's considerably bigger than this cube, but that means it only will last for 30 or 40 years. Oil resources are a bit more. We also consider fracking resources. Coal are even more. So some people say it's about 200 years that the coal will last, but there is still the problem with the greenhouse gases and the global warming. Some people say the nuclear power is an alternative, but if you see with all the world would use nuclear power, the uranium resources would be very quickly depleted. So what we can do, we can use solar energy, and it's quite interesting. This big yellow cube, what you see here, represents the solar energy that hits the Earth's surface during 1 year only. So it's much more than all the resources we have for all times together. So remember in the first slide I told you this has been created during a period of hundreds, exactly 150 to 200 million of years, the age of carbon. This has been created. During that time also the solar irradiance has been the same. So you have to multiply this big yellow cube by 150 millions or 200 millions, and the outcome is rather poor. This is the resources we have. Okay, we used up a considerable part of them, but still it's a bit disappointing. So the conversion from solar energy into carbon resources is rather poor. If you compare that solar irradiance during 1 year to the world's energy consumption, you have a factor of 14,500. So the solar irradiance hitting the Earth is 14,500 times higher than the world's energy consumption during 1 year only. If you would apply technology, rather conservative estimate, we use photovoltaics, evenly spaced with a total efficiency of 10% only. We would need, you see the continent of Africa here, and we placed also all our solar panels on the Sahara Desert. So there is no agriculture there, there are no people living there, so it's not harming the nature there. And we would need this area equivalent to supply the whole world with solar energy. For Europe, this square would be considerably smaller, or for Germany and Brazil have about the same energy consumption. It would be almost invisible from the satellite perspective. It's not very favorable to place all the huge solar power plants at one place. We can distribute them. That also eliminates the needs for storage, because if we go along the different latitudes and longitudes, we have power all year long and for day and night. Because we place it around the planet, we have sunshine at least of each one of the power plants. You have to interconnect them to a global supergrid. The costs of that, including photovoltaics, would be about 20,000 billion euros. That's not cheap, but then you would have sustainable energy forever, or as long as the solar modules live with it nowadays in the vicinity of 30 years. The total power needed for that, equivalent of output power of nominal power of photovoltaics, is about 18 terawatt. So see here. Here you see the different irradiance level, what we discuss today. So the red part, which occurs here along the equator, represents for constant power flow 350 watt per square meter day and night equivalent. Where we live here now, here in Germany, it's in the vicinity between 100 and 150 watt per square meter constant power flow, irradiance power flow. So the costs of renewable energies 10 years ago, also research by NREL, this was estimated that the costs will go down to 3-4 cents per kilowatt hour, which is US cents per kilowatt hour for wind, and it was estimated for photovoltaics it will go down to 20 cents per kilowatt hour. The reality shows otherwise, so we already reduced it already in 2018. It was already 2 cents in the sunniest locations per kilowatt hour, and even in Germany it was less than half of that given or estimated, that 20 cents per kilowatt hour. And if you go to 2020, we have now at the sunniest location, or not even at the sunniest location in Portugal, the last tenders were sold for 1.5 cents per kilowatt hour. And in Germany, the last tenders have been in the vicinity of 4 cents per kilowatt hour. So it's a total success story for solar energy, because the prices are now in the vicinity of really thermal energy. If you burn gas, you have also most the same cost of energy as this 1.5 cents what the tenders in Portugal. Let's talk about the sun. So the sun is a great energy source. It has a power output of 4 times 10 to a power of 20 megawatt, so enormous power. And We receive the sun is quite the Earth is quite far away, about 150 million kilometers. That's not in scale. We will see in scale a little later on. And also the size of the Earth is much smaller than given here. We will see also later on. Also, the solar irradiation we perceive on the Earth isn't take place in the center. This is rather hot there, about 15 million degrees. And this radiation would cause a black body radiation, which is a very harsh X-ray and wouldn't allow life on Earth. Fortunately, the sun is only radiating with a relatively cool surface of itself. This is called the photosphere, with a temperature of 5,800 to 6,000 Kelvin. And this is generating that spectrum. A great physicist named Planck has developed that formula. Says you can directly, this depends directly on the temperature. If you have higher temperature, the spectrum is more rich in energy and it goes down to shorter wavelength. If you have colder temperatures, the spectrum is getting more reddish and it is shifted more towards longer wavelength. And this method is even used to determine the surface temperature of faraway stars, because you can measure the spectrum and by this you can measure the surface temperature. This also this method to do that is developed by an Austrian physicist called Wien. It's called Wien's law. And so just if you have the maximum, you have automatically the temperature here. We talk about solar irradiance, not about sunlight. Light is only usually the visible part of solar irradiance. And this starts at 400 nanometers and goes up to 800 nanometers in wavelength. On the right part of it, or towards a longer wavelength, this is called infrared radiation. If you have shorter wavelength, it is called ultraviolet radiation. And this is just the visible part which where actually the most energy is emitted. If you take a look at what share of irradiance is arriving on Earth, so we take a relation between the distance and the different diameters of Sun and Earth, we come to a value of 178 petawatt. That is 10 to a power of 15 watts. Now let's take a look at the real scales. So that's actually the real scale, not the real distance, but the real scale of Sun diameter and Earth diameter. The diameter of the Sun is 109 times larger than the one of the Earth. If you go to the distance, you come to this representation. So this is Sun, and here it's quasi invisible, the Earth here. And this is the scaled distance here. You have an angle of about 1 degree, which is captured from the Earth. So you see the Sun is only 1 point, but it chooses it's 109 times bigger than the Earth. It's also not in scale, but it explains very well the astronomical situation we have. So we have two rotating axes. One rotating axis is the Sun, the Earth around the Sun. And we have another axis here, which was formerly a very long time ago in parallel to the first axis. But due to a very large impact, and by this opportunity the Moon has been created, so the impact was by a planet almost the size of the Earth. This axis have been tilted by a value of 23.5 degrees. So these axes are not in parallel anymore, and the consequences are the following. So if you have, like nowadays in summer, almost summer, at the 21st of June, the northern surface is more illuminated by the Sun. It's tilted more towards the Sun. So we have summer here on the northern hemisphere, and the opposite is at the 21st of December. Then the southern hemisphere of the globe is tilted more towards the Sun. So it receives more solar irradiance. And therefore we have summer on the southern hemisphere, and while the northern hemisphere is tilted away from the Sun, we have winter on the northern hemisphere. If you have the 21st, it's a maximum elongation or maximum tilting towards the sun. We have perpendicular irradiance at latitude of 23.5 degrees north of the equator. And if we go to the 21st of December, we have a perpendicular irradiance at 23.5 degrees south of the equator. If we talk about the equator, the sun hits perpendicularly on the equator at the 21st of June. It's also called equinox because the northern and the southern hemisphere receives the same amount of irradiance, and also the duration of day and night is all the same all over the planet. It's all 12 hours. The same occurs to the 21st or 22nd of September. This is not fixed because we don't have a fixed we don't have an even number of days for 1 year. It's 265.25 days, and therefore in some years it's the 21st, in some years it's the 21st of September. One important value is the so-called solar constants. That is the value that of solar irradiance that hits the Earth on above the surface, with a value of 1367 plus minus 7 watt per square meter. It's bouncing a little bit because it's not a complete circle, it's a little bit elliptic, and also you have some measurement inaccuracy. And this is the amount of irradiance that the satellites receive if you're circling around the Earth at a relatively low orbit. Talk about the different naming of the angles. So we have the elevation angle of the sun, called gamma S. S stands for sun, gamma is for the elevation. If we also want to express the deviation from north or from south, some literature they use the deviation from south. We use the standard, the German industry standard 53.5 part 2. This is all the deviation from north, which is also like a conventional compass. It also gives the deviation from north. And this is given as alpha S, alpha for azimuth and S for sun. In some literature you also find the zenith angle. So it's a counter angle here from the elevation angle. So if you have here 90 degrees, and 90 degrees minus gamma S is the so-called zenith angle. We have the atmosphere, and the atmosphere is absorbing the light, not evenly. It's absorbing the different parts of the spectrum in different ways, and therefore it's important to know how thick or how long the path lengths of the sun rays through the atmosphere are. So the shortest is if the sun is perpendicular on the Earth's surface. That doesn't occur in Germany, but as I told you, between the equator and 23.5 degrees north and south of the equator, we have at least some parts of the year perpendicular irradiance, and this is called air mass 1 because the way through the atmosphere is once, and if you have for all different angle, it's longer. For example, if you have an elevation angle of 41.5 degrees, this is AM 1.5. You can calculate that by AMX as 1 divided by the sinoid of this sun elevation angle. Here you see the influence of the surface temperature. As I mentioned already, the surface temperature of the sun is almost 6,000 degrees. So it creates a spectrum of this kind with a maximum in the vicinity of 500 nanometers or 0.5 micrometers. If the sun would be a bit colder, it would create that spectrum, or even more colder, 3000 Kelvin is about what a light bulb can reach a maximum, depending on the material you're using. Then you have a maximum at the at 1.0 micrometer. That's already invisible because we only can perceive irradiances up to 800 nanometers or 0.8 micrometers. So this is all infrared radiation. So it's less a light bulb, it's more a heat bulb if you consider the real efficiency. So it's only about 5% of a conventional incandescent light bulb is visible light, 95% is infrared radiation. This is a bit amplified by a factor of 10, otherwise it would be rather small because the temperature, the formula you saw before by Planck, the temperature is by a power of 4. So this is again the black body radiation of the sun, and 150 kilometers apart from the sun at the Earth's atmosphere, above the Earth's atmosphere to be exactly, so the solar constant, or also called AM0. We have this spectrum, almost the same as the black body radiation, and if you pass the atmosphere here, what you see here with a length of 1.5 or AM 1.5, you have this spectrum. So you see a large part of blue part, and ultraviolet is missing. Also we have some dumps here due to vapor and other aerosols and gases in the atmosphere. Can continue that for different air masses. So we start at the equator for the equinox. That means at the 21st of March and 22nd or 21st of September. Then we have perpendicular irradiance at the equator at midday, so 12 a.m. Then we have a sun elevation angle of 90 degrees, and that's equivalent to AM 1.0. If we wait for an hour and 20 minutes, we have an elevation angle of 70 degrees and AM 1.06. So the spectrum is already a bit deformed. If you go on to 230, then you have an elevation angles of 50 degrees only. You see that first the total density is decreased, but here is a missing blue part and ultraviolet part, but also here some reduction, but not as severe as the ultraviolet and blue part. And if you go down to almost sunset, so sunset at this time of the year and the equator is 6 p.m., so 40 minutes before sunset, we have this spectrum, so almost nothing of blue is left and nothing of ultraviolet left. So a lot of it is infrared and a large part is red, and that's a typical sunset red. These are some examples for different dates in Berlin. So in the winter, at the 21st, 22nd of December, we have an elevation angle of 14.1 degree in Berlin. That's equivalent to AM4. The values for Paderborn, you just have to add 0.6 degrees to that. That means we would have 14.7 degrees. That's equivalent to the latitude difference between Berlin and Paderborn. If you go to summer, so the highest position of the sun is reached at the 21st of June. We don't reach perpendicular irradiance because this is only, as I told you, 23.5 degrees north and 23.5 degrees south of the equator, so we don't reach it in Paderborn. And there the maximum elevation is 60.8 degrees for Berlin plus 0.6 degrees in Paderborn. And these are the different parts of the year also. If you plotted this for a whole year, you come to this graph. Let's start with winter here, 21st of December. As we just discussing some seconds ago, at midday, we have an elevation angle in Berlin of 14.1 degrees or 14.7 degrees in Paderborn. That's, you can see here, this is sun elevation angle, gamma S in degrees. And here the solar azimuth, that means in the south, so midday the sun is directly in south position. If we go on in the year, perhaps nice to mention is also that the sun goes up at 8 a.m. and goes down already at 16 a.m., so rather early p.m., so 4 p.m. or 16 o'clock. If we go on in the year, so we are now close here in March, April, so we have the sun positioned almost 40 degrees elevation angle. The sun already goes up at 6 o'clock and goes down here at 18 o'clock. So we have exactly equinox, so it's 12 hours days and 12-hour night. If we go to the 21st of June, so we have the maximum position, as I mentioned already, a little bit above 60 degrees in elevation angle, and sun already goes up at 4 a.m. and settles only at 20:30 p.m. If we go to other locations, for example here Cairo, it has a latitude of 30.1 degrees, so that's not within this plus minus 23.5 degrees of the equator. So still there is no perpendicular irradiance, but we're pretty close. So at the 21st of June, the elevation angle is 83.4 degrees. The lowest position is 36.6 degrees, so rather higher than in Germany. You see also in these graphs that the duration of the days are more similar than in Germany, and sun is rising pretty quickly, even in winter. So this is now a little bit a different representation of Rio de Janeiro. This is a polar coordination, so we have the horizon is here, this outer circle, this is the horizon, and the middle is here the zenith, and you have here the different elevation angles you see here. And here you see that because it's directly on the circle of 23.5 degrees, while it's on the southern hemisphere, it's south, and you see we reach perpendicularity here at a certain date, and that's here in summer on the southern hemisphere, that's the 21st of December, and here we reach at midday perpendicularity. The lowest position is reached at the 21st of June, so winter on the southern hemisphere, and you see it's a little bit 42 degrees. This is a formula to calculate that, so maybe you can program an app also, or there are also different apps on the market. I used this formula now from the German industry norms, which I mentioned already, 50,034, part 2. And the first part is the formula for the azimuth alpha S. So you see it depends on the elevation angle of the sun, and the elevation angle of the sun is given here, which depends on the latitude, but also on the sun declination. So that's the sun's position at midday in relation to the equator at this certain date. And then you have here also for this gamma, this depends also on the number of dates, starting with day 1, 1st of January, up to day number 365. This is D. And T is the number of the hour of the day. It starts at midnight 0 and goes to 24, and 12 is the highest position. With you can also consider the refraction by the atmosphere. So this is from the Earth. This is from the Astronomical Almanac, which considers the refraction. And if you have angle above 15 degrees, this effect is rather low, but as lower as you get, this effect gets more severe. And this is the adequate formula to this. It also depends on the temperature of the Earth's atmosphere and so on. And yes, if you want to really do a very exact calculation, you may consider that. We have different types of irradiance. So this is diffuse and direct irradiance plus albedo. So above the atmosphere, the extraterrestrial irradiance, there is direct irradiance only. So if you are in space, you see only the sun as a point, and the rest of the sky is totally dark. And if you are on the ground, you see, due to the so-called Rayleigh scattering, that the sky is blue. This is a part of the original direct irradiance, which is scattered, and this is now called diffuse irradiance. Additionally, you have some reflection from the ground. This is called albedo. You won't see it if you have a horizontal surface, but if you have an inclined surface, what's often the case, this plays a considerable effect, especially if you have high reflective surfaces like snow or water. There's a thing called global irradiance. This is a sum of direct plus diffuse plus albedo irradiance. Just to give a quick overview to you, a quick approximation. So if you have a dark clouded sky, you have an irradiance level, it's a rule over the sum, from 50 to 200 watt per square meter. If you have light clouds, it's from 200 to 700 watts per square meter. If you have a really clear sky, it may go up from 700 to 1000 watt per square meter. This happens rather seldomly in Germany. Even at very clear sky, it's quite hard to go above 900 or 950 watt per square meter. These are some examples here. This is recorded diffuse and direct irradiance in Cairo during 1 year. So you see here the maximum is reached close to 9 kilowatt hours per square meter per day of accumulated irradiance during 1 day. See here, largest part is by direct irradiance. Only about 20 to 30% is diffuse irradiance. In winter, it's still the average about 3 to 4 kilowatt hours per square meter per day. Okay, there are some really bad days where you have diffuse irradiance only. It may go down to 1 kilowatt hour per square meter per day. If you compare it now to Berlin, you see first there's a much higher share of diffuse irradiance only. And if you consider the highest points, it may reach 8 kilowatt hours per square meter per day. But the critical part are the lowest irradiance levels, which go down below half a kilowatt hour per square meter per day, not only for a single day, but for a couple of days. And this makes 100% solar power supply in Germany rather difficult. Either you have to superdimension your PV generator quite a lot, so this gives enough supply even during winter, or you have to think about a seasonal storage. That's now under discussion, so-called power to gas. So you have here, for example, hydrogen produced during summer, which you may use up during winter and re-electrified via gas turbines or fuel cells. But we come to this in lecture 10 and 11. These are some extremes. They also actually measured also in Berlin. So we have for winter, 28th of December, it's a really sunny day. It doesn't look so bad here. So irradiance may go up to above levels of 200 watt per square meter, but very close to that, only a week apart, the irradiance is rather low and you have very low irradiance levels. If you compare it to a sunny day in summer, so you have here, as I mentioned, 1000 watt per square meter is very hard to reach, but a clear day may reach 900 watt per square meter. Here you see the differences between horizontal measurements or horizontal receivers, like for example a pyrometer, which is mounted usually horizontally, and the tracking. So it means that you have a plate which looks always perpendicular to the sun, so that it's tracked either by hand or automatically. You see here, for example, if we start at December, 20th December, so if you track your photovoltaic module or in general your receiver, you will see that even in December the sun is rather low, but if you track it properly, the irradiance level received can be rather high. If you have a horizontal mounting only, you see that the irradiance level, even at a clear sky, is rather low because the elevation angle of the sun, as I mentioned already, 21st of December is only 14.1 or 14.7 degrees in Paderborn, and therefore you lose a lot of irradiance due to the horizontal position. In summer, that difference is not as big, so it's quite similar because the sun is elevated. So remember, a little bit above 60 degrees. And so the difference between optimally tracked and horizontally fixed is rather small. But in the morning, for example, if you track it towards east, you have a high difference. And this is now, if we talk about energy transition, rather important, because we have almost too much power during midday, but power is missing in the morning and the evening hours especially. And if you track your PV generators, you may generate more power in the morning and more power in the evening, which is helpful for the grid operation and reduces the necessities for additional storage or backup power. Here are some daily irradiance values for different parts of the world. So we have above here the Sahara Desert. So lowest is December, because in the northern hemisphere, lowest is winter is in December and January, but it doesn't go below 4 kilowatt hours per square meter even during winter, and the highest is 7.5 kilowatt hours per square meter. It's quite evenly distributed. If you go to Spain, you see here, this is also not so bad, a little bit shifted towards downward. So the lowest is 2.5 kilowatt hours per square meter per day in winter, and highest is almost as much as the Sahara Desert, so a little bit below 7 kilowatt hour per square meter per day. Then we take a look at South Vietnam. So from the latitude, it should generate more, but we have a lot of clouds and a lot of rain. So there's a rain period, and the maximum level in the summer don't reach as high here as, for example, Almeria. Then as another example, we have London, UK. You see here that equivalent to Germany, the lowest values are really low in the vicinity of 0.5 kilowatt hours per square meter per day. The highest is still quite low, not as high as in here, it's quite low, about 4.5 kilowatt hours per square meter per day. So in Berlin, this is a bit more. Here's some examples for Brazil. So first we have Hamburg in Germany, as I mentioned you, minimum even below 0.5 kilowatt hours per square meter per day. Maximum not so bad, 4 kilowatt hours per square meter per day. And these are several locations in Brazil. I lived there for a while, so I have a lot of data from there. And the red line here is Rio de Janeiro. It's phase shifted here because we have summer in January and December and winter here in June. So lowest irradiance is pretty much equivalent to the summer in Hamburg, in the vicinity of 4 kilowatt hour per square meter, but summer there the average value of irradiance reaches almost 6 kilowatt hours per square meter per year. If you compare it to Hamburg, it's much more evenly distributed. So difference between summer and winter is much less, and so you need much less seasonal storage if you would need it at all. Porto Alegre, another example here, is more south, 30 degrees south of the equator, and you see here that the seasonal differences are much more pronounced. So in winter we have 3 kilowatt hours per square meter per day, and summer it goes up to a little bit even above Rio de Janeiro in the vicinity of 6 kilowatt hours per square meter per day. Fortaleza is very close to the equator, 3 degrees south of the equator, and you see here the irradiance level are really high all over the year. Only here's some rainy season in April, therefore there's a dip here in irradiance values. Let's go back to Germany. This is a map for Berlin. Here we have on the y-axis we have the elevation angle of the receiver, and here we have the azimuth angle of the absorber of the receiver in angular degrees. Usually, according to the German industry, this should be 180 degrees, but as you see, there are different representations here. So this is another literature by Mr. Quashing. So he just chooses azimuth at 0 degrees for south. Just take care of the literature. This is not definitely defined here that south is 180 degrees, so here it's 0 degrees. Elevation angle, that's clear. 30 degrees is a quite good optimum here, a little bit below 30 degrees, and you will receive here irradiance value, accumulated irradiance value for all over the year of 1,100 kilowatt hour per square meter per year. If you elevate the modules more, you will see, for example, if you have a south facade, the irradiance value would go down to a little bit below 800, maybe 750 kilowatt hours per square meter per year. That's okay, that's about 30% less or almost 40% less, but you have to consider that it's orientated strictly south and has a very high elevation angle. That means it captures very well the winter irradiance. So the irradiance distribution during the year is much more equilibrated than if you would have the optimal angle, which produces a lot during summer but very little during winter. So you see here the azimuth, if you go there plus minus 5 degrees, it doesn't make a big difference. Formerly, people were positioning their solar modules very accurately with a compass and so on, because also photovoltaic has been very expensive. But nowadays, some degrees difference don't make a big difference in yield and cost. So let's take a look in Europe. So the red star what I marked here is Paderborn. You see that is all green, and this is the equivalent yearly irradiance in kilowatt hour per square meter per year. If you go to the green, you will see here that Paderborn has in the vicinity of 950 kilowatt hours per square meter per year. Berlin, as you see here, is a bit more. It's about 10% more of solar irradiance. Best in Germany is Freiburg with about 1100 kilowatt hour per square meter per year. This is for horizontal irradiance. And so the best position in Europe, for example, here we take, there's some even more, but if you take a very good location in Europe, it's for example Seville in southern Spain. There we come to about double of that value, 1,700 to 1,800 kilowatt hour per square meter per year of annual irradiance. Let's take a look at Seville. Here you see that this is now monthly irradiance. So if you have a horizontal mounted system or horizontal receiver, you have irradiance during 1 month of 78 kilowatt hour per square meter. If you incline that module a bit, for example by 30 degrees, then you have a considerably higher irradiance during that month. So it's about 30% more, 112.6. And as I mentioned already before, winter is the critical time, so you have to superdimension your system or supply seasonal storage. And just by the inclining, this helps already a lot. On the opposite, if you go to June, then the best position is horizontal. If you incline the modules, you will lose some irradiance values here during 1 month. But first, it's not much, and then usually you have a surplus in summer. In total, you have small advantage with an inclined surface at 1,944 kilowatt hour per square meter per year, in contrast to horizontal irradiance of 1,757 kilowatt hour per square meter per year. If you would incline more, this value would go down, but there would be even a higher advantage in winter. But this is about the maximum for having maximum annual yield. So some other irradiance maps found by ERC, maps all Europe, but also from Africa. You see here that you have a global irradiance if you go to Johannesburg in Southern Africa, which goes to values above 2,000 kilowatt hours per square meter per year. So more than double than in Germany, up to 2,600. Already, this is a quite interesting scale here. This is already calculating the solar electricity in kilowatt hour of electricity generated by kilowatt installed of nominal power. Therefore, this is index P of 1 kilowatt of power plant at nominal test conditions. But we come to this a bit later. Also, this depends very much on outdoor temperature, spectrum, and so on. So this is not totally correct, but gives a quick rule over the thumb how the achievable energy yield during 1 year is. It's also mapped all over the world. Usually the system designers, they use a software called Meteornorm, the Swiss company, which supplies for every location annual, weekly, daily, or even hourly values of each point of the Earth. I think they have 7,000 stations, and in between they interpolate from the 3 nearest stations. How we measure irradiance. This is either by satellite measurements or, what is more accurate, by ground measurements. And this is a so-called Pyramometer. This is frequently used by meteorological stations since almost 100 years. It works, the principle is rather simple. So you have an absorber plate. First you have some glass domes here. That's in order to avoid heat loss by wind and so on. And the essential part is here. This is the thermal absorber. And by the absorption of solar radiation, this heats up and is warmer than the compensation device. So you have a temperature between those 2 black plates here. And in between you have a thermopile or a seebeck element, which generates voltage, as you see here. And if the device is properly designed, you have some proportionality between this seebeck voltage and the actual irradiance or the global irradiance. The value is rather low, so you have to amplify that voltage considerably, or you use several seebeck elements here. Usually you do both. You have several seebeck elements plus an amplifier here to amplify that voltage. Another method is to use a solar cell as a radiation sensor. It has the advantage it reacts very quickly in contrast to the Pyramometer, because the heating up of the absorber takes some time. Formerly this took minutes. Nowadays it's only seconds, so about 5 seconds until the absorber reached its final temperature after a radiation change. But the actual semiconductor sensor is much faster. It goes in microseconds, adapts to the different irradiance conditions, but also it's much cheaper and smaller. But the problem is it only sees a small part of the spectrum. For example, in the case of silicon, the main sensitivity is around 800 nanometers. It doesn't see any irradiance below 400 nanometers and doesn't see any irradiance above 1150 nanometers. But if you use solar generator of the same technology, for example, also silicon photovoltaic solar generator, this is rather helpful because then you can estimate the yield quite good by such a silicon sensor pyrometer. But if you want to do really good objective neutral measurements, the pyrometer is the way to go. The silicon sensor is, if you go to the photovoltaic effect, we will repeat that. So it's converting incoming photons into a flow of electrons, and this flow of electrons is proportional to the irradiance value. So the flow of electrons is a current, electrical current, and this is directly very good proportional to the incoming irradiance. And you can convert that current into a voltage by a shunt resistor and then measure the irradiance value. This is a setup, some example of a setup. So you have here the pyrometer for measuring global irradiance. So irradiance can come from all sides, either direct from the sun or diffuse from the sky, or even albedo. If it's a bit inclined, can measure. This is registered here or recorded here. And these 2 other instruments are more specific. Here on the left side is this tube, which is directed directly to the sun and measures direct irradiance only. And this is the opposite. So you have a shadow ball which allows that the pyrometer sees everything but the sun. If you amplify this a little bit here, you see it. So this is a shadow ball. It has to be always repositioned, so it always casts a shadow directly on the pyrometer, and there it allows to record diffuse irradiance. This is a counterpart here, the measurement of direct irradiance. This always be positioned, so this device is rather expensive. It has to be very accurately positioned to follow the path of the sun. And this is a little bit cheaper device by a Swiss company, which automatically considers direct and diffuse irradiation by complex shadow masks and different sensors on the ground, and computes by that by the contrast the different levels of direct and diffuse irradiance. This is our roof here. As you see, the measurement setup here, a pyrometer to measure global irradiance. This is a self-made pyrometer which measures also global irradiance, but you have more specific spatial measurements. So this only sees a part of the sky, and we can see the distribution of irradiance within the sky. Here are some other measurements for wind speed, and this is for precipitation and for humidity and temperature. This is for precipitation, and this is for humidity and temperature. You see some modules, not now it's fully equipped here. There are a lot of modules here, and also we test the microinverters here. So we come now from the sun, so the positions of the sun, sun's elevation angle and azimuth. We come now to the receiver, and we have also some definitions for the deviation from north. This is called alpha E for German Empfänger, for the receiver, and also the elevation of the absorber here, gamma E. This is indicated here. And this is a normal to the surface here, to this blue surface. And this is the position of the sun as a sun. So as you know before, this is the elevation angle of the sun. This is the azimuth angle of the sun. And this is the actual incidence angle of the sun to the normal of the, or the perpendicular vector of the surface of the collector. And yes, this is the equivalent angles here also. This is 90 degrees minus this elevation angle here. So this plus this is 90 degrees here. And this is the azimuth angle, and here from the normals to the zenith angle, this is also the elevation angles of the absorber. Can do quite complicated calculations by that, considering obstacles, so on. There are some simulations programmed to do it, which I will show you a little bit later. And for example, here you make just a setup of the different obstacles you have here. So here at a position of 20 degrees, you have, for example, here a house at an angle here. Now he's considering, yes, this is 180 degrees from north. So this azimuth angle at 200 degrees azimuth, for example, the chimney and so on. And you can copy that outline of the obstacles to the line of the graph of your sun during a day and the year, and you see here that in winter this is particularly the obstacles are particularly reducing your possible output still until 21st of February. In March, up to 21st of March, we don't have any problems. The obstacles don't harm anymore, they don't shadow anything, and for the whole summer until to the equivalent day in autumn. Also, there is some auto shadowing. For example, if you have a large PV generator, one row is not enough. You have installed several rows. It's not critical if in summer, because the sun is rather high, as I mentioned already, 60 degrees above the horizon. So there is no shadowing here. But in winter, when the sun is rather low, for example, 21st of December, then we have only an elevation angle of 14.7 degrees in Paderborn. And then the shadow cast is rather long and you have to maintain a very large distance. A rule over the thumb for Germany is that you have to keep a distance of 4 to 6 times the height. It's a compromise between the energy loss to the shadowing and area loss. So if you have to keep a very large distance, you have to purchase a lot of land in order to install your PV power plant. Or you do both, agriculture, and so the distance doesn't matter so much. We do an exercise to that, and I want to explain you first how this works. So this is these are the 2 rows here, what we have as a cross section. So we have the first row here with an elevation angle of gamma E and a height of h, and the length of the module or the collector is L, and the distance between the 2 rows is D. You split that up into D1 and D2. So we have some perpendicular triangles here. So this is the first triangle defined by the hypotenuses L and the height L and D1. And the second triangle here, this is a hypotenuses, and this is D2, and again the height H. This is the optimal position. So the sun is here and the second row is exactly not shadowed anymore. If the sun is lower than that, for example here, then here if you go to H half, then half of the module area is shadowed and you have a loss in energy production. Let's do an example here. So we have here H is defined by here L times sinoid of this angle here. So it's just basic trigonometry, so you have it in school. And here you have D is equivalent to D1 plus D2. D1 is here L, the hypotenuse is L times cosine of gamma E. Or you can express it differently with Pythagoras. So it would be here L in square is the sum of D1 square plus H1 square. Or if you want to express it in D1, D1 is the square root of L square minus H square. D2 is here H divided by the tangents. So the relation between the counter angle and the closer angle of alpha. So H divided by tangents alpha. So we have this stays the same, and you have here the H substituted, and you have here L times cosinus gamma E plus L times sinoid gamma E divided by tangents alpha. Or you do the same way via the Pythagoras sentence. And you have here the same result, but expressed differently. And you can already calculate that formula you find in some formula books here, but now you calculate it manually here. Okay, these are some simulations during the year. So we take, these are the elevation angle of your modules, as I mentioned already. For an optimal energy yield in Central Europe, you would take a value of about 30 degrees. This is the shadowing angle, the actual elevation angle. If you go to winter, for example, maximum for the midday at the 21st of December, it's 14 degrees, or in the vicinity of 15 degrees, for example. Okay, it's 15 degrees in Munich, so it's a bit southern of Paderborn and Berlin, so it would have this angle. And if you combine those two values, you come here to a land use area of about 36% of your land use, if you keep the distance to keep that is not shadowed, at least during midday. If you elevate your modules more, then you will have a lower use of area efficiency. So see, you're going in this direction, then the use of area is going down. Same applies if you would decrease your shadowing angle. Here you have the relative shadowing losses during a whole year and also the elevation angle of your receiver or your solar module of your solar collector. Take the same values, also 30 degrees, and we take also the same shadowing angle of 15 degrees. We come here to a value of about 6% of relative shadowing losses. If you would put the modules flatter here, for example here to 5 degrees, you would have lower shadowing losses, but altogether less energy yield, especially during winter. So just will explain you the first exercise. First, in order to do the first exercise, you have to know some certain expressions. First is the so-called nominal power output of a PV module. We will discuss it in detail at the lecture for photovoltaics. And the electrical power output is defined at a given solar irradiance of 1000 watt per square meter at perpendicular irradiance and a spectrum of AM 1.5 and an operation temperature of 25 degrees. And these conditions are called standard test conditions. If you operate a module under the standard test conditions, it will give you in the maximum power point your nominal power of a PV module. To indicate this power value, this is an index P given. I've been showing you that already at the map for the South African irradiance value. So this is small p. That means we have 1 megawatt at these conditions. If you have, for example, half of the irradiance, you would have about only half of the power output only. But this depends also on temperature and spectrum and so on. So for the first exercise, we have to just consider, we have to think about the distance between two rows of PV modules in order to avoid shadowing at least during midday for the whole year for a module elevation angle of 23.5 degrees, which is also the latitude of the location, Rio de Janeiro, which is 23.5 degrees south. Thus the module has to be directed towards north or south? That's the first question. Really quite easy if you think a little bit about it. The requirements for midday of the day with the lowest sun positions of the year, the direct irradiance should not cause any shadowing by the front rows, so the lowest non-shading angle alpha. The modules with a nominal power of 300 watt each have a length of 2 meters and a width of 1 meter. Which of those requires less space? Horizontal or vertical mounting? What would be the area need for 1 megawatt peak nominal of installed power? What would be the relative saving in required area if the module elevation angle would be at 10 degrees only? So that is your homework, and we discuss the results or the solutions in the exercise. Thank you very much.